G'day guys, a pretty quick video here for chapter or exercise 1.5, graphing straight lines. This is really the introductory stuff. We get into a little bit more detail in the next one, but let's jump straight in. The gradient of a line, a measure of how steep the slope is. Remember, rise over run, change in y coordinate divided by the change in x coordinate between two of the points on the line. That's the way we usually find it. What are the important things to remember? We can see down here, they sort of got the intercepts out of order. We'll come back to those. Positive gradient, going uphill from left to right. If you're feeling positive about things, you're feeling up. Negative gradient, the red one there, downhill from left to right. If you're feeling down, you're feeling a bit negative. That sort of makes sense. What about this horizontal line? It's got a zero gradient. Why is it a zero gradient? Well, if we think about it, rise divided by run. Is there any rise in a horizontal line? No, so the rise would be zero. What's zero divided by a number that's not zero? Zero divided by anything else is zero. So the gradient of a horizontal line is zero. The vertical line, I don't like this term here, so we're going to talk about that. They've said the gradient is infinite. Now that's not a great descriptor. The problem being, yes, it sort of approaches an infinitely large number as we get more and more positive or more and more negative. The problem is if they're both approaching, if you imagine taking that positive line and making it more steep, or this negative line and making it more steep, they're both approaching that y-axis there, both approaching a vertical line. Is it becoming infinitely negative or infinitely positive? That's a good question. It's a question we can't solve in maths. So we have a specific term we use for the gradient of a vertical line, and it's not infinite, it's undefined. So please make sure you're aware of that and take care of that. That's something we've got to watch out for. Don't believe everything you read in a book. The second thing we look at when we're graphing straight lines, we already talked about y equals mx plus c. C is the y-intercept. The y-intercept. How do I calculate a y-intercept? Whatever the equation is, I let x equal 0. If you substitute x equals 0 in, you'll be able to find the y-intercept straight away. Same with the x-intercept. If you want to find the x-intercept, anywhere along that x-axis there, you'll see that the y-coordinate is 0. Y tells me how far above or below the x-axis I am. If I'm on the x-axis, y equals 0. So to find the x-intercept, you substitute in y equals 0. They talk about a couple of special lines here. We've talked about y equals mx plus c, c being the y-intercept and the gradient. Horizontal lines, we now know gradient of a horizontal line is 0. So the equation, y equals c. It's only the y-intercept that matters because you can see that red line there, which has been called y equals c. Everywhere along that line, the y-coordinate stays the same. The y-coordinate's always whatever c is. So if it was y equals 3, that's a horizontal line through 3. Y equals negative 2, a horizontal line through negative 2. Pretty straightforward. Vertical lines, same sort of principle. The x-coordinate is always the same for any point on a vertical line. So if it goes through B, then the equation's x equals B. If it was a vertical line crossing the x-axis at negative 2, the equation would be x equals negative 2. And finally, I'm not sure why they're stressing this, but if you've just got y equals mx, there's no c. That implies c equals 0. Where would a y-intercept of 0 be? Oh yeah, at the origin. So it's not particularly surprising that for those sort of lines that pass through the origin, the equation's y equals mx. I want to have a look at just one last thing. I'm going to show you Desmos. Some of you may have used Desmos before, some of you may not. Here's a good example of y equals mx plus c. I've got m equals 1 and c equals 1. Why does c affect the y-intercept? Well, let's have a look. As I slide the value of c, that'll change the value of c. So here with the c being, if I can coordinate my mouse movements a little bit better, here where I've got y equals mx plus c and I've got m equals 1 and y equals 1, y equals x plus 1 in other words, you can see the y-intercepts move to 1. As I slide this y-intercept and make it larger, this c value larger, oh look, the gradient, the y-intercept is increasing by the same amount. C equals 5, the y-intercept equals 5. The gradients stay the same. The line is just shifting up and down, and you can see as I move it up and down, that point, the y-intercept moves with it. Pretty straightforward. Let's have a look at that gradient. We said that it affects the slope, the m value. I'm trying to get that at 1. There we go. As I increase the M value, what should happen? More steep and more positive. So if I increase it, yes, it's still going uphill, but it's steeper, isn't it? Look, a gradient of 3 is actually quite steep. Yeah, and as I get steeper and steeper, it's getting a larger number. The number's becoming larger, the gradient. If I continue going closer to this vertical line, that number's going to increase much more quickly. Similarly, if I get a gradient of 0, we should find that horizontal line that we were after. Let's have a look and see. Oh yeah, there it is. When the gradient's 0, horizontal line. As I take the gradient to the negative side, we'll see it's filling down, it's going downhill. That's a negative gradient. Simple things to remember that shouldn't give you too much trouble. If you have a look at what's coming up in this exercise, deciding if a point is on the line, substitute in the values. If the equation's still true, it's on the line. If the equation's not true, it's not on the line. That's pretty straightforward. How would I sketch using the gradient intercept? Here we've got y equals 2x minus 1. Rather than looking at their solution, let's go to Desmos and see how I would do that one and how you could do it as well. So the equation we're trying to sketch is y equals 2x minus 1. So if I chose a point, the y-intercept is -1. So I'm just going to put a point in at -1. How would I do that? I'd say the x-coordinate is 0 and the y-coordinate is -1. And you can see that point's turned up there now. If I wanted to choose another point on the line, if I was going to sketch this, y equals 2x minus 1. Okay, so the gradient's 2. So I'll just turn that off a bit so we can see. If I go up 2, a rise of 2, and then a run of 1, because obviously it was up 2, 2 is the same as 2 divided by 1. So I need that point there, which is actually 1 and 1. So if I include another point here, 1, 1, I reckon that my line's going to go through those 2 points. So I plotted the intercept, use the gradient to go up 2 and across 1, get another point, then I connect them up and I've got the line. So let's see if y equals 2x minus 1 really does go through those points. And bang on, it went straight through those points we expected. And so you would just draw your line through those points, put a little arrowhead on the end of it, and you're done. Anything else exciting in this exercise? Well, if you want to find the x and y intercepts, we've already talked about that. X-intercept at y equals 0, y-intercept, looked at x equals 0. Then you go ahead and solve vertical and horizontal lines. We've covered those. So you're ready to get stuck into the exercise. There's no hot maths for this exercise, so just get stuck straight into the classwork. You've got your little list here of which questions to do. And don't forget, you can also use your homework time tonight just to catch up on those other questions that you haven't finished yet. All right, good luck. Cheers.